All right. Here we go.
Wow.
It is the Grapevine Show.
How'd you get all four of us in here at once? That's some fancy stuff.
I've been practicing.
5
minutes before the show. All right. If you're new to the Grapevine Show, I'm Chris Hughes, host. Eric Kaiser to my right here, co-host. Michael Cianfranco, bottom right there, also a host. And we have a special guest tonight, the man, the myth, the legend, Mr. Steve Rogers, president of the Energy Conservatory.
Hey, everybody.
Hey, to the show, Steve.
Good evening, sir.
Yeah.
All right.
Coming on, man.
So, before we jump into it, tonight's going to be a pretty awesome show. I've actually done homework, which is not like what I do weekly. We all know. So, I've got some slide decks put together. It's going to be awesome. Eric, did you do your homework?
Dude, I don't do homework. I just show up.
Come on, man. I literally sent a text out yesterday. I said, we need to have a killer show. I want to have a killer show. Let's all take a topic and dive deep. Michael, I'm staring at you. Hell, even Steve put something together.
I did a little bit.
I
didn't do no slideshow, a PowerPoint, but I wrote some things down on the old whiteboard and got a couple of things versed out. Yeah.
Good stuff. Well, before we get in, how's the weekend?
Good, man. Good.
Good. Steve, solid weekend?
Yep. Got the range hood installed.
Oh, yeah?
Can vent outdoors now, not back into the kitchen.
Nice.
Dang, that sounds like that was a pretty big job. That's not like that's cutting a hole through the cabinetry going all the way up, so you cut the roof out? Shingled roof?
No, it went through the wall.
Oh, okay.
Oh, you lucky man.
Yeah.
You lucky duck, you.
Range hood's right up against the exterior wall, so I just went up and out.
Oh, nice. Yeah.
Sweet.
Nothing wrong with that. I don't ever get that lucky over here.
Did you have a cabinet there, or did you have to go use an escutcheon up through the cabinet?
It's through the cabinet. So the cabinet lost a shelf where the duct comes up, but it was
gotcha.
It was a sacrifice worth making.
Yeah. Yeah.
We sacrifice that cabinet for spices every time
That's right.
In my area, y'all do the same thing where the duct goes up and through. That cabinet becomes the place where all the spices go.
Yeah. Yeah. Mine got I've got vaulted ceilings right there. So I had to make like a fake, make it look pretty. Because I'm not a metal guy in South Florida, I use flex duct.
Yeah, ain't nothing wrong with that.
I see Eric shaking his head. Nah.
Wait, you ran your range hood in flex duct.
Yeah.
Man, you don't want to do grease duct in flex.
I know, man. I know.
That's a mess.
It looks like it's metal duct.
When you say you ran it in flex, are you using like what we would call running regular duct in that type of flex, or like the metal flex that I've seen people use for that? It's like a little bit more heavy duty.
Question. You know what it reminds me of? The inside of flex duct, the inside tube. That's what it reminds me of. But it was silver.
Oh yeah, I think you got the heavy duty stuff.
Yeah,
I know what you're talking about.
It doesn't matter because Italians boil everything; they don't fry anything.
That's right. That's right. We're not greasing.
You grease outside. You know what I'm saying?
I made eggs this morning, so I smoked the bread on there real nice.
They were poached, right? Not fried eggs.
Yeah, that's right. Yeah.
Well, peanuts are in season over here. I'm just saying. I just boiled a huge sack of peanuts, and I just froze them. So
what is this? Can you explain this to me? This whole southern
peanuts?
Bayou. Yeah, what
man.
Are you doing?
So you got to find the right sauce. You know what I'm saying? So like I had to go to the grocery store. It's I took a picture of it. Oh, Swamp Fire. That's the name of it. It's called Swamp Fire. It's got a raccoon and an alligator on the package.
Yeah, it drove me crazy. I go, what is he sending me in this group message?
Yeah.
That's what I want my peanuts to taste like, is a dead raccoon and a dead alligator.
Yeah. This does not taste good.
You don't
we
know.
need?
All right,
We
I'm
need
bringing.
swamp fire.
So I was talking to my dad because we go to the symposium every year, and we go to the house, and I was like, we should boil a
be
whole
good this
sack
year.
of peanuts and bring them down there, and then everybody who comes and hangs out, we just let them leave with a bag of peanuts.
I like it.
Yeah,
I don't want no swamp in there.
Just call it roadkill surprise, right?
that's right.
Roadkill peanuts.
So,
I didn't know you could kill a peanut on the road.
because it literally takes forever to boil peanuts and get the shell soft. It's very time consuming. All right. So on to the show because this is going to get heavy tonight.
Oh man,
Go
Yeah,
first.
'cause
are you going to
We-
make us think on a Sunday night?
Play paper, rock, scissors for it. Who
we got to
wants
get
dibs?
going because we talked for half an hour last time.
Yeah,
about
we
food.
All right. Come on, Eric. Batter up, dude. You do.
Batter up?
Yeah.
What are we talking about?
Things you thought you knew. HVAC edition. Round number
Oh,
one.
Man,
Things
so
you
this
thought
this,
you knew.
this was a recent dive of mine. Was down instrument accuracy as well as compounding accuracy.
Oh, was this when you were on the
Yeah, I mentioned
podcast?
this. I mentioned this on the ESCO podcast.
Let's go podcast. Yeah, I shared that, man. That was cool.
Yeah. So
All right,
I
let's
did
have it.
I did a dive into some test instrument accuracy and was looking at, okay, so we've used for years analog gauges and some thermocouples. So I just grabbed the accuracy of an analog gauge, grabbed the accuracy of a thermocouple, just an off the shelf that a lot of technicians are going to use. And when I when I looked at the two accuracies, there's an accuracy. Each kind of test instrument has an accuracy range. Some of them are listed in a percentage of the reading. Some of them are listed in percentage of full scale reading. There's a ton of different ways to show accuracy, and Steve probably can do all the math. That's not me. Steve's the math whiz.
But you're discussing what was in the article I wrote for the NCI publication last month or the month before. Yeah.
Oh, really? Interesting.
Yeah, percent of full scale versus percent of reading, and how do you equate the two? Because you have to do math to figure
That's
out.
cool.
which
You
one's
guys
better.
are on the same wavelength.
Yeah.
Well, what I figured out was, so like when we use analog gauges and a thermocouple to do superheat and subcooling, we have to deal with the inaccuracies of two instruments instead of just one, because we're actually using the reading from two different instruments to figure out what the superheater subcooling is.
Mm-hmm.
And
superheater subcool is often a subtraction, right?
well, it is. So we use the pressure from the pressure gauge to find our saturation temperature on the PT chart of the refrigerant that's in the system. And then we use the line temperature to see either if it's above or below that saturation temperature. So if the temperature is below saturation, then it's subcooled. If it's above, it's superheated.
Yeah.
Now we're dealing with the inaccuracy of a pressure gauge to find our saturation temperature, and then we're dealing with the inaccuracy of that temperature gauge, and just straight up calculated inaccuracy. I did a 410A at 100 degree line temperature, 110 degree condensing temperature. It was a plus or minus 4.8 degree range.
On the taking the pressure inaccuracy and how much that affects the saturation temperature.
Well, so the pressure inaccuracy, so it's a potential range of plus or minus 4.8. So what I did was I laid the two ranges over each other, right? And say the pressure range or the pressure range was plus or minus 2 degrees based on the accuracy of the gauges, or the saturation temperature was plus or minus 2 degrees. And then the temperature range was like plus or minus 2.8 degrees, or maybe it was vice versa. I don't remember which one was which. I don't have the slides in front of me. But what it comes out to be is if the temperature gauge is reading all the way at the bottom of its range and the pressure gauge is reading all the way at the top of its potential inaccuracy range, you end up with 4.8 degrees between those 2 points. So you have a total of potential inaccuracy of 4.8 degrees on a 10-degree subcooling reading.
So it could be
Yeah.
14.
Plus or minus 48%.
Right. So if you're
at
good
least-
with 48%,
Wait, is it plus or minus 48% or is it plus or minus half of that? Because it's from the middle up or down, so it's plus or minus
Yeah.
24%.
I'm curious about the same
24.
question. Are we saying it could go down 4, it could go up 4, or 2 and 2?
Right.
it could go down 4.8 or up 4.8
Up or
degrees.
down. Yeah.
So plus or minus
Oh.
48%. Yeah.
Yeah.
Which what you're telling me is if you've looked into some of the charging charts, and I'm thinking of one right off the top of my head. I remember looking at. I want to say it was a Comfort Maker, and it said plus or minus 3 degrees subcooling.
Right.
So-
like
2 to 3 degrees is normally your range on most manufacturers' charging
Right.
charts that I've
So
seen.
you're saying that our analog gear cannot
Does
put it-
not meet manufacturer.
does not meet
specifications.
manufacturer specifications.
You got it.
Interesting.
You got it.
Wow.
And that kind of blew my mind because I'd never really thought about it in that way before. And I was actually doing the presentation when you and I went down to A-Care in Alabama.
Yeah.
And I started looking at the inaccuracies on this stuff. And it really made me think about it a lot more about, hey, what are we actually doing here? Versus I ran just some digital, again, I just picked out a set of off-the-shelf digital gauges with their ratings. And I'm just using the published ratings here because if you're putting sensors on top of dirt or maybe a corroded line set or something else, that's a whole different set of inaccuracies because, there can be other problems there as well. Or if you're in the direct sunlight with your sensor.
Do you know of any research that the line temperatures are coming from actually measuring the resistance of the copper? Is that correct?
Well, it depends on what sensor you're using.
Yeah, I was
I
going to
think
say
the field
there's
piece does
algorithms,
that, right?
So the field piece, what do they call it? They have a specific name for that probe, and yes, it uses the conductivity of the copper to complete the circuit on the thermocouple.
Because I got to clean the copper up really good for those.
Yeah.
Right. You should clean the copper up for any temperature reading you're doing on copper because
That's
you
true.
don't want that corrosion or any dirt or anything on top of there. You want a good contact.
Yeah.
And the rapid rail. Thank you, Brian, right there. So the rapid rail sensors use the conductivity of the copper. That's why you have to clean it up really well. Now, if you look at a thermistor or a standard thermocouple, right, they just lay on that surface and they just use a surface conductivity.
Like the Testos are a K-type.
So do you know, has anybody done research to find out even if we get the temperature of the copper perfect, how different is the temperature of the refrigerant from the temperature of the copper?
I don't know as anybody's done exactly that, but it's pretty darn close unless you have your sensor in direct sunlight and then the ambient temperature and that radiant heat from the sunlight heating up that temperature sensor from the backside will screw your readings all up.
Yeah, I've thrown like a rag over it. I keep a rag in my bag when I'm doing temperature readings for subcool. And I just put it on there because that heat, man, in summer down here, it's killer.
Well, a lot of times what I do is I'll take you take the electrical panel cover off of the unit.
Oh, that's a good idea.
And just lay it right over my sensors.
Little doghouse. Yeah.
Little kind of doghouse.
I was talking to someone at Testo. Y'all would know him. He's been on the circuit for a long time, and he was telling me about the math that goes into the sensor being embedded into the handle, and when the handle clamps to the line, because only some of that sensor is touching that line, and the rest is encapsulated in plastic.
That's right. Yeah.
That matters to the equation. I guess they have to offset for what's the temperature the plastic going to potentially be. With the sensor. I don't know the math, but he said it's more goes into it than what you would think.
If I'm a technician, listen to this podcast, right now, it'd be
you
like
are a technician.
I am
listening to this podcast right now.
You're a technician on this podcast right now.
Speaking for a friend, not me, But I mean, what's the silver lining here? Like, talk to me, man. Like, should I bring ice cubes with me every morning? Check my thermocouple on the
There are certain gauges. There are certain thermocouple probes out there, and this is one of the things we have to read the manufacturer's directions for our tools, and we need to understand the tools that we're working with, because there are some instruments out there that if you unplug a say there it's got two thermocouple probes.
Yeah.
Now I want to delineate between thermocouple and thermistor here real quick. The thermocouple probes, thermocouples of course generate their own voltage when the heat changes, and we read that voltage in the meter, and that is a whole nother problem right there sometimes. Now
and that's the testos.
Do you know about cold junction compensation with thermocouples, Eric?
Woo, that's a good one.
Yeah, no, not enough to talk to you probably.
Because
we got to go there now.
Because a thermocouple doesn't change its voltage with temperature. Its voltage changes with the difference between one end of the thermocouple and the other end. So wanting to know the temperature at the business end where you're trying to measure the temperature, you have to know the temperature at the other end of the thermocouple.
Okay.
And so, which means if the end where you're taking your reading is at room temperature, you should know what the room temperature is. Otherwise, it throws off the reading at the other end of the thermocouple.
Wow.
So very often they will have built in, the cold junction, which is the one that you're not trying to read.
Like an ambient?
So
at ambient temperature, but it
Wow.
matters if it's ambient temperature on a 90-degree day or ambient temperature on a 70-degree day. So
Right.
usually there will be another temperature sensor on the cold junction, so you know what temperature the cold junction is. So then you can calculate the temperature of the the hot junction, or the junction that you're trying to measure the temperature with.
The sense junction, basically.
Yeah.
So in other words, you probably want to keep your meter, whatever that is, out of direct sunlight as well.
Yeah. Well, unless, I don't know, you do have to take one apart and find out, is there another temperature sensor in the handle, or how is that done?
Right.
Yeah, I'm not sure on that. That's a great question, because I hadn't really looked into how the meters actually read this stuff. But so there are some thermocouples out there and some instruments that you need to calibrate each input to whatever thermocouple you're going to plug into that. And if you plug a different thermocouple into that, like say you just grab a different sensor off your truck and plug it in, you need to recalibrate that input on the meter.
Yeah.
And when you're calibrating, water and crushed ice, not just ice cubes, crushed
That's
ice.
what I was going to ask you, man. I took my clamp and I grabbed that ice cube. I was like, oh, wow, it's a little off.
No.
Is anybody grabbing random sensors and throwing them on meters though?
Well, so say you've got a meter with two inputs, right? And you have two clamps. If you flip-flop those two clamps, if you have a clamp labeled A and a clamp labeled B, and A is calibrated to the A input and B is calibrated to the B input, and if you flip-flop those.
But
you're saying like an old Testo manifold with the two clamps for sub.
I'm saying like anything. Okay, anything
I'm a visual guy
that a K-type thermocouple on it, which is the little yellow plug with the two different size spades that plug in.
Now, Eric, are you talking about type K to type J, or you're talking about just one type K to a different type K?
One type K to a different type K plug. So if it's calibrated to plug A, basically everything we use in the field here is going to be type K. There's nothing else other than K type. So if you plug K type that you calibrated in plug 1, if you unplug that and plug it into plug 2 on your meter, you may need to recalibrate your meter, but you don't know unless you actually test that.
Yep.
Gotcha.
See, I prefer to put.
Here's another thing. All right. Thermocouples, right, which we use a lot of, K-type thermocouples. Again, that's that little yellow plug that's in all of our meters,
right,
that we plug in with the two flat long. They're about a 3/4 of an inch long flat metal pieces on the end.
Gotcha.
Those are sensitive to spurious electronic emissions.
So what does spurious mean?
Spurious.
I think tonight's challenge is to use as many words as you can that most people don't understand.
Okay.
And go.
So this is electronic interference that comes out of things like TVs, EC motors, frequency drives,
the sun,
which is things like variable speed compressors.
Oh, like the back EMF?
No, not back EMF.
Okay.
The back EMF
Microwave ovens.
Yeah, they put out electronic radio wave emissions, and
Okay.
it's
damn right. This is a hilarious show you got.
so they all put out electronic emissions, and some of them are in the radio wave spectrum, but some of them are a voltage, and they will induce a voltage. And it's kind of like walking under a set of high tension power lines, the big cross country power lines. And if you hold a fluorescent light tube up at night, you can actually light the tube up.
Oh, I just did that this weekend.
Yeah, you too.
Yeah.
I
So
was doing that when I was boiling peanuts. I was out there with a light bulb.
because
Little rave party.
the thermocouple is a voltage based device, you can actually change the temperature reading on your meter if you have stray emissions in the area.
So now I know how to mess with my helper.
But
Just bring a microwave out there when he's doing subcool.
hold it right next to the meter.
Yeah.
But you don't know, you have no idea if those are happening. I
Wow.
ran across this by accident in the field one time. It was, I can still remember it. It was on an old Lennox pulse furnace, and I had my K-type thermocouple probes crossing the meter leads that were reading flame signal on that furnace. And at the end of my test, I would unplug my jumper leads that were going to the flame sensor to simulate a flame out and make sure that it closes the gas valve and as a safety check. And when I did that, I was watching I happened to look over at my temperature meter. All right.
And you were cooking a burrito?
No, because I was monitoring supply and return temperature to get my delta across the furnace.
Gotcha.
Okay. I looked over at my meter, and when I unplugged that flame sensor, my temperature dropped by 10 degrees on my
Damn.
K-type thermocouple meter.
Wow.
Wow.
And I'm like, this is not cool. And I've seen it a couple other times. I've been able to recreate it a couple of times in the field, and especially around inverter units.
Oh, right. The inverters really.
Because they
Crazy.
they're changing that voltage. Well, EC motors will do the same thing because they're taking that AC, they're making DC, and they're chopping that DC up.
That's right.
And
That's
I've
sine
had
wave.
them
Yeah.
affect televisions.
I wonder if that's what's causing some of the communication issues you hear about all the time on the 2-wire communication going from indoor to outdoor.
It's possible, but unlikely, because those are tested in the environment with those inverters and things like that.
Right.
Chances are it may be something else, like maybe that 2-wire is running next to an AC power line for a long distance. If it's running next to or parallel to an AC power line for a long distance, you get
So let me ask you a question.
Or it's next to another brand, and the other brand uses a different chopping frequency.
Oh,
and we
wow.
didn't test for that chopping frequency.
or
Yeah.
that. Yeah. I mean, there's
Oh, that's
all
super
kinds of
interesting.
things.
Yeah, I didn't think
Yeah.
about that.
So
No.
You have two inverters right next to each other. You're right.
the other
And they're
option,
connected to the same ground too, right?
Exactly. Yeah. And then
Well-
the copper line set is running through the ground. Who the hell knows?
so the other option for temperature sensors is thermistor based temperature sensor,
Okay.
which is a resistance change rather than a voltage change. Yeah, I mean, some people are doing shielded, some aren't. RS-485 doesn't necessarily play with shields all the time.
Some manufacturers don't want the shield, and some manufacturers specify they do want the shield.
It depends
And-
on their communication protocol.
It does, but I know a lot of people who are moving to shielded cable.
Yeah.
Wow.
Just even though the manufacturer says do not do it, or
And if you're going to go to
recommends
move
not
to
to do it.
shielded cable, you better understand grounding the shield or draining the shield, because it's actually a
Right.
drain wire because
No
it's
kidding.
capturing all that extra signal, and it's draining it to ground. So it's technically not grounding it. It's actually a drain line.
Only
so
connected
right.
at one end or the other, but not both.
Right.
Oh, I did not
Right.
know that.
Yep. You have to connect it at a single and closest typically to the ground connection.
Chris,
Or the
do you have a
Like-
graphic with
like
a
Cody
rainbow
says, or you get an antenna.
with
Yes.
the more you know slogan? You got one of those? No?
I should have
Okay.
built it in the slide deck.
It's
All
got to
right.
have a little
Great.
star at the end of the rainbow.
Eric's batting a 100 out of 100 right now. It's pretty awesome stuff.
I didn't even prep for this. Remember,
Oh,
this
thanks
is
a
just
lot.
crap that rolls out of my
That's
brain.
exactly what I wanted to hear before I was going to go into mine.
Yeah.
It's like I didn't even prepare. No slides, no nothing. 100%. Go ahead, Chris. It's all you. So, all right. I'm Mike. Unless you want to go.
No, go ahead, brother.
All right.
He's got
So-
slide decks and everything. You want
Yeah,
to
this is
follow
gonna
that?
be fun.
Slide it
I always
up.
like to play a little game with things like this. Now, I'm just gonna throw it out there. This was built in like the last 2 hours, so I didn't like sit here and like, hey Steve, why don't you double check this for me, make sure it's all right before we go public with it. Not that situation. So
Don't worry, I'll be sure to tell you in the most public place I can.
That's right. Yeah, he's pretty good at that. Yeah, Steve's good at saying, Chris, nah, part's not right. Yeah, kill it.
That's
All
hilarious.
right. So I got my slide deck. Then we'll go to Steve's slide deck. So here's my slide deck. Steve, you can't answer
Yeah.
because
Well,
I
let's-
didn't know you were coming on the show tonight.
Let's clarify the question though. So the same amount of leakage spread evenly around both houses, meaning they both have the same CFM 50.
Yes.
Same CFM 50.
Yeah.
Yes.
Okay.
So I'll read it just for everybody. If I were to have two houses, one that's 8 foot tall and one that's 16 foot tall, with the same amount of leakage area spread evenly around the houses, right? Both having a 68-degree delta in the winter. My infiltration on the taller house will be blank than that of the short house.
Can I add one thing to the question here, Chris, just to make sure that
Do
we're
that.
no, I just I don't want people to think that we have one house that's tighter than the other. So let's say that the
Right.
taller house is a little smaller, so like the shell area is the same also. That'll make it a little easier to
Gotcha.
understand, I think. Yeah.
That
That doesn't have to be the case, but
Yeah. I actually walked this all the way through with load calcs and everything. So
okay.
Woo!
I went there. I ain't playing around. I
So
brought
do
it.
we get to make guesses now or what?
Yeah. So
All right.
let's let the chat
Yeah, let the
do their
chat roll.
thing. So we got one person for A. He says that the house will have less infiltration than the short house.
Less. We got less. All right.
All right.
So
Anybody else?
There's a more.
There's a more.
There's a same.
All right. C. Same. All right, Eric, you go ahead.
I got to go with B.
More. Okay. Michael,
I'm going with more.
you're just copycatting Eric.
For the taller house, right?
Yep. Steve, I'm not going to let you answer.
Yeah, mute his mic.
Yeah, we'll mute him out.
He owns the energy conservatory.
All right. Here we go. So I broke C-Stack down again. I've only broke it down quite a few times. So Steve,
What the heck is a C stack?
oh, okay. That's a good point. So C-Stack is a
It was the
program.
map of the monster on Land of the Lost in the 70s.
That's right. And then has evolved into a computer program. But so C-Stack is a program at the Energy Conservatory. You can download it from our website. And it will let me see if I'm going to say this just right. It will estimate infiltration based on different parameters that you input to the program, like height of the house, CFM 50, which is the leakage of the house, temperature of the house from indoor to outdoor, and your ventilation strategy, or whether that be all exhaust, balanced exhaust, you get the point. And it will show you your neutral level pressure plane up and down. So it's heavy. It's a heavy program, but it's easy to use when you learn it. Steve, did I miss anything?
No, this is good.
Okay. So I tried to break it down again my way. And so I went and grabbed one of my loads from Quick Model. And I started playing around when I was doing this. And so here we go. We got a house that I'm going to call loose, right? And the reason I don't call it like average loose or anything like people might know from Right Soft is because I'm comparing two houses and I'm just calling one loose, one tight. So the ACH 50 of this house is 5.7, which I would call loose, right?
That's loose.
The CFM 50 is 2,000, right? Ceiling height 8 foot, and the square footage is 2628. Now, for fun, I went ahead and put 2 sheets of paper over here to describe the CFM 50 of 2,000 to say, like, what's my leakage area? It's about the size of 2 sheets of paper, which just to give you some concept of how
Two
much
sheets of
leak-
paper. That's how big the holes in the sides. You know, if you add up all the holes, how big they are, right?
Correct. Well, yes, exactly. So we've got 2 sheets of paper worth of holes. Now, in the program, when I enter this house data, I've got a 1-story house, 2,000 CFM 50, right? I've put my temperature, even though this is kind of covering up. Anyway, that temperature says 0 and it's 68 degrees in the house. I slid the temperature to 0. Our flow in and out of the house is 107 CFM naturally. Steve, you want to give them the explanation on that?
On the why the natural is different than the CFM 50?
No, just to
Or-
give them the why is it 107 CFM? Like what's happening there? Temperature
Oh.
drives pressure, pressure drives flow.
Yeah, exactly. So you can see in the diagram from CStack, the temperature at the top of the house is 2.2 pascals, and the temperature at the bottom of the house is minus 2.2. And that's approximately what you're going to get if your leaks are evenly distributed. So if you got that much pressure, and then we've got this 2 sheets of paper worth of holes scattered around the whole outside of the house, then this is a calculation of how much air will go through all those holes. So with 2.2 pascals of pressure and 207 square inches of holes, you're going to push about 107 CFM in and 107 back out.
All right. There's your explanation. So in this loose, short house, we've got 107 CFM. Then I mocked up the same house. This is what's interesting. You'll notice the ACH 50 went down to 3, which would make you think tight house, right?
Wow. Look
But
at
the
that,
CFM
bro.
50 stayed the same. We still have 2,000 CFM 50. What does that mean? That means
That means we got to
still
get
have-
rid of ACH 50. We got to get rid of it.
Well, we still have 2 sheets of paper worth the size of holes in the house. The house just got taller, like Steve said earlier. Same single height, same square footage, but now our flow has went up to 167 CFM from top to bottom.
What did I win?
Yeah.
So,
We-
so to
we
answer the
can-
question,
We could stay on the show another month.
that's right. You've earned yourself another week in the pilot. So
But look at why. So look at those pressures at the top and the bottom of the house. So it was 2.2 before. Now if the house is twice as tall, the pressure is now twice as much. So you got minus 4.4 at the bottom and plus 4.4 at the top. So you got twice as much pressure pushing through the same amount of holes. You get more airflow.
So you
So
get
essentially
more of
there's
like a skyscraper dynamic with it. With
Exactly.
a taller
Yeah.
house.
So
So
there's
I'm going somewhere with the whole end of this, but
Uh-oh.
yes, because we still got more
We
to
got
go.
a hand up. We got a hand up.
We got a hand up. All right.
So there's an 8.8 pascal pressure differential between the bottom of the house and the top of the house with reference to outside. Am I reading that right?
Well,
I
There-
would say way to understand that is from the center of the house, you've got 4.4 differential from the top of the house to the center.
Yeah,
And the
that
same thing from
neutral
the center to the
pressure
bottom.
point is very important. What am I talking about?
I
I
mean-
learned that from the guy down below me.
Same here. So yes and no. I would say yes
So
and
there-
no.
there's not an 8.8 Pascal pressure anywhere that you can measure with reference to outside. You can
Right.
measure plus 4.4 and minus 4.4. So yeah, the difference between the top of the house and the bottom of the house is
But
8.8.
if you ran a hose from the top, a reference hose to the top and a reference hose to the bottom, you would end up with 8.8 differential between those 2
Yep.
points.
Yep.
Okay. That was my
Yeah.
that was my query on that.
That reminds me of the Angry Ed. He did that in his house.
Hold on, guys. We're still going. You ready?
Go, baby,
I
go.
ain't even got to the good stuff. All right. So will
Drop that
the difference in flow of 60 CFM change the load calculation?
It
All right, I'll
better.
let the chat. All right, it might be an easy one. All right, Michael, you
So
go
what
first.
do you mean? Will the difference in flow of the natural leakage?
No, will the difference
He-
in flow from the tall house to the short house, will it change the load calculation?
if
Whoa,
they blow or door exactly the same, and one's
right.
tall and one's short, is that going to affect your load calc?
In manual
Yeah.
J, I think it's ignorant to it. I would say no.
Okay.
I'm going with Michael on this one. I'm going to say that Manual J does not properly look at this.
All right. I was going to give the chat just a minute. We got a few. Let's see. We got 2 yeses. We got a plus or minus 70%.
And I think C should say it should.
All right. So here is the data that I cranked out before the show. This was done in Quick Model. And I modeled the house just as such, but I will say this. Let me think about that for a second. The house grew taller. Man, it's a lot of data to look at.
So
I gotta remember what I
you
did
are
there.
able to put in a ceiling height somewhere, right? That's
I raised the
Yeah.
house of the whole ceiling.
Right.
So
So
you
I
just-
doubled
you just
the
raised the wall height.
volume. I doubled the volume of the house, which
You
is
just-
why the ACH 50 changed.
Basically, you
3.
just raised your wall height. You didn't change you didn't put a second floor on it or anything.
No, I just changed the ceiling height. And the program did change. What's weird is I colored all this to perfection, but when I entered it into StreamYard, it ate up the colors, which is weird. This was all supposed to be matchy. But anyway.
So I
Um,
got a question then, because if you had 2628 square footage with an 8-foot ceiling height and a 16-foot ceiling height, how come you didn't get, because essentially you're doubling your volume.
well, or is that 2628 square feet on 2 floors? In
No,
which
that's
case it's a smaller footprint.
I raised, so to Eric's question, it may not, I was rushing, so it's not proportionally perfect because the load calculation I was at, first off, didn't have 8-foot ceilings. It had a little bit different. C-Stack is built to have 8-foot, 16-foot. And I think you could even do a 3rd-story floor on the program, right, Steve? You can go
Yeah.
8 again. The house I had modeled wasn't at 8-foot. I just doubled the house that I designed. So don't take it.
So it's
That
got a
granular.
2628 footprint. Well, no, because my question is,
Yeah.
why did the ACH go from 5.7 to 3.0? If you double the volume of the internal space, it should cut the ACH 50 in half. In my brain, the way I'm thinking about it.
Oh, that's because, sorry. Go back one. So I estimated when I was building this slide, so that was probably 2.9 or somewhere in that range.
Okay.
So
All right.
anyway, but to answer the question is, our capacity did go up, or not our capacity, the capacity we need to feed the home has
That's
went up.
good.
Infiltration
So-
load went up. Yep.
Infiltration load went up, and a better pictorial of that was what I kind of threw together here, kind of showing the loose and short house in comparison to the loose and tall house. So the loose and short house, let's look at winter load, about 10,000 BTUs, and then the winter load on the taller house went to 14,000 BTUs. So essentially, if you have the same leakage area, but the house got taller, you're going to have more infiltration.
That's amazing. Look at that difference, man.
So let me ask this question. Here's the bonus lightning round question. There's more difference on the winter load than the summer load. Why is that?
Oh, I know the answer to that, but I'm going to be quiet.
I think I can answer that.
All right, let's give the chat a chance.
It's a good answer. It's a
Steve,
good- I
throw
like
that out there again for the people in the chat, and let's see if somebody can nail it.
Yeah. So the winter load difference is almost 4,000 BTUs and just over 800 in the summer. So you got what was that 5 times more stack effect
That's a big
difference. The much bigger difference in the load in the winter than in the summer. And why is that?
Well, We've
I
got
think- I
Michael
think-
House saying it's more of a TD.
That's
We've
what
got
I'm
HVAC
thinking.
No, I
overtime.
think he
saying
means, he
DL
means touchdown, right?
Yeah, we've got Delta T from HVAC overtime. Looks like I think everybody's kind of getting it here.
What's your design
He's right.
temp?
It is a difference in temperature from indoors to outdoors, and there's more delta in the wintertime than there is in the summertime.
But you said it early on. Temperature drives pressure.
That's right.
That drives flow.
Mhm.
All right, so there's that. Hold on, I'm not done.
Uh-oh.
It's better. All right, if the leakage, man, the StreamYard does not pull in PowerPoint very well. If the leakage
Mhm.
area was not spread evenly, meaning the leakage was more at the top or the bottom of the house, what would happen to the infiltration? Meaning, A, does the infiltration go up? B, does the infiltration go down, or does it not move? Or C, does the infiltration go up?
For what
Let me
season?
just to clarify the question again. We're still talking about the same house that blower doors out at 2000 CFM 50.
Yes.
Okay.
So we've got Neil says, did we say where the house is?
Man, I
I
thought
can
that was
actually-
Comparetto again.
So I can actually answer that. because I was looking for close as I could get to a perfect 68-degree winter delta, and I found it in my design load with Missouri. I picked Missouri and some other state in a county inside Missouri. So that's
So
where the
let's say
house-
all the
that's where
examples
model-
are in Missouri, right?
all the examples are in Missouri on this situation.
Yeah.
All right, so we got Mike Barnes in here. He says leakage at top goes up. Oh, are we talking about wintertime or summertime? That's a good question. We are talking about wintertime. Like I said, this was a rush build, so bear with me. But it's a fun one. All right, Eric, I'll let you go first. Take a
We're
stab.
talking about
Yeah.
winter time, and that may or may not matter.
I'm gonna
Yeah.
say A.
All right, he says A, the infiltration will go down. So, Mike, you want to take a stab?
You're saying that the leakage was more at the top or the bottom. What would happen with the infiltration?
Yeah, basically, you know how we talked about we have leakage area, and earlier we said it's all spread around the house evenly.
It's all spread evenly.
Now we're saying it's not spread evenly, meaning
Okay.
more of the leakage is either at the top or it's at the
Oh,
bottom,
okay.
but it's
Okay.
not evenly at the top and the bottom.
So you're leaking
So-
more through the ceiling into the attic, or you got a house with a crawl and the floor is really leaky.
So I
into
remember
the
what
crawl.
Jenry was telling me. Jenry was saying if it's more in our market, it's all AC. So if our leakage is at the ceiling, that's what we have to attack the most in Florida, because it makes it so that attic temp at 140. So I would say more. If you're going to put that leakage top or bottom, I think it would extrapolate it more. I'm
All
sticking
right.
with that. Final answer.
Final answer. All right, good stuff. All right. Dum-dum.
Now I'm sweating.
So the answer is you have less flow,
Shit.
less infiltration when your leaks are at the top only or at the bottom only. Top would be on
Really?
the left, bottom would be on the right. When you have equal flow top and bottom, you're going to get more flow. And that's what showed in the center. So the answer is, seal one of the top of the bottom.
Because when your
Right. Okay.
holes get closer together, you're effectively shortening the wall height, which we already know when you shorten the wall height, you have less stack effect, which means less leakage.
Well, Steve,
Right.
you
let's-
have the best explanation for this.
That's
which
what
you
I was
gave me
trying to
one
say.
time.
Jenry was saying in our market to seal all the ceiling ones. So that's what he means. He means attack the ones on the ceiling.
So
Well-
let's look at the one on the left. You want me to give that explanation?
I think so, Steve. You
Chris?
do a very good job with this. One time you explained to me well about how the hole could be big on top, but if the hole at the bottom is small, you can only push so much air in the bottom hole.
Yeah, and that's why the neutral pressure plane moves. So look at the left slide carefully. Notice that the neutral level's way up. The neutral level is going
Right.
to find wherever it is that I've got half my leaks above and half my leaks below. So because the one on the left has more leaks near the ceiling, that neutral level, it moves up. So wherever zero is going to happen in that house has moved up to find like the middle of all the leaks. So you could say that, we've got 206 square inches of leakage area. So there's 103 of them above the neutral line and 103 of them below.
Okay.
Right. But we said in this case, 103 of them are high near the ceiling. So that means that the neutral level goes up. But when the neutral level goes up, now look at the pressure at the top of the house, 0.9. Pressure at the bottom of the house, 3.5. So the reason the leakage goes down is because the pressure is lower where there's more leaks. And at the bottom of the house, the pressure is higher where there's fewer leaks. And you could take this to an extreme. Let's say the house is built like a bathtub. It's hermetically sealed at the whole, all the walls and the floor are hermetically sealed like a bathtub, but the top is still leaky. Well, where's the neutral level going to be? It's going to be at the top, which means the pressure at the top will be zero, which means the leakage will be zero.
Oh, wow. That's cool.
Yeah.
Dude, that's a mind experiment right there. That's
yeah. You got to think about.
You're taking my best practices takeaway away from me.
It's like taking the bottle of soda and putting a piece of paper on it and hold it upside down.
Right.
The water can't leak out because there's no place to let air in.
Yeah.
All right. Let's see what else I built because I may have something else in there. Oh yeah, look, there it is. There's the house if it gets taller. Same situation. I just wanted to show what would happen even in the taller house, which you'd get the same situation. You would get more flow with equal leakage at the top and the bottom. And
what am I looking at
less. Here? You're looking at the 16-foot house that's taller. You've got more flow. We've established that right in the center. But I added this to the house on the left and the right to show that if the leakage is not balanced, then you would get less flow. Because we drive the neutral pressure plane up or down.
So the first one on the left, that's where most of the leakage is where? On the bottom or the top?
One on the left?
On the top.
One on the
yeah.
Because your pressure differential is lower. Your larger holes are where your lower pressure differential is.
Neutral level is high, so that means most of your leaks.
Yeah, most of your leaks are up high. The neutral level lose more to where more leaks are.
Okay.
So,
all right.
Cody said something important here. So Cody said the pressure is greatest when the neutral boundary is farthest away from the top and the bottom. So another thing that's interesting to point out is that riffs off what Cody just said. If you got 50% of your leaks at the ceiling and 50% of your leaks at the floor, let's say the walls are tight, that's actually the worst case for leakage. That's the most leakage you can have is 50% up high and 50% down low.
Mm-hmm. Which you could check this with a manometer, and an accurate manometer that reads pascals. Or you could do it with you could take a DG8, stick a hose out of the top window and at the bottom of the door downstairs and check pressures and then do a little math. Or take it like a DG1000 and run two reference hoses, one from channel A and one from channel B, and leave the manometer in the center of the house.
So, and if you go on our website, there's April of 2020, there's a video of me doing this in my house. And I measured the pressure through the highest window and the lowest door on two different channels. But then I opened the basement door and that made a big leak down low. And you can actually see the pressures move when I opened the door.
I remember watching a video of him explaining this on YouTube, and my brain hurt for a week.
Well, you can watch this one again.
Yeah.
Hope it's better now, Mike.
All right. For the essence of time, I'm going to rock and roll because Steve still got something juicy. All right. So best practice takeaway. Assuming the leakage area in the house is spread out evenly, where would be the first best place to begin air sealing the house? Last question. All right, I'm going to let the chat go for it, and then we're gonna let Michael go first. We'll let Eric go first, and then we'll let Steve answer. So we've got an A. We got one guess. That's it. All right.
I'm
right.
going.
All right, go ahead, Michael. You going with A? Top? Okay.
I'm
All right,
gonna
Eric,
go-
what do you think?
I'm going to go with C.
Oh, nice.
Either and C being either the top or the bottom, depending on the construction of the house.
Oh, I thought you meant yes.
Yeah. Steve, you want to take it, or you want me to take it?
I would answer it. Well, first of all, there's no option C here.
I know.
So, but I'm going to say the top or the bottom, whichever is easier to do.
Yeah, I was gonna say both, A, B, or both, because we just talked about it, guys. We were talking about seal one side, move the pressure plane. All right, so that's my best practices takeaway. That's my hour and a half
So
of homework before the show.
Let me point out that the answer is not at the center, and this is also a reason why replacing your windows doesn't make a big difference, because the windows are usually kind of near the neutral pressure plane.
Right.
Very, very.
So, yeah. So
And-
they don't have a big impact on the leakage. a lot of
And
time.
going from like an R1 or 2 window going to an R4 or 5, what is that getting me? A whole lot
Well,
of nothing, right?
And you got to look at the solar heat gain coefficient too. The R
That's
value,
true.
and especially in your neck of the woods, if you're dealing with cooling loads, if you go from a solar heat gain coefficient of 0.8 down to 0.2, you make a huge difference.
Yeah.
All right, guys, Steve's turn. You ready, Steve?
Yep.
Steve's best practices. Here we go.
So, Chris, we don't have a ton of time left. We should
know.
either talk about deadband and cycle time, or we should talk about the other stuff. I think let's just talk about deadband and
I
cycle
say
time.
do it all because you could take my time.
We can
we'll
always,
we'll
run
take
over
Michael.
a little bit.
Yeah.
We'll take up Michael's time.
I ain't got
This
nothing.
is juicy.
So first of all, let's define what is the deadband, because different manufacturers of stats will call this something different. I have an Ecobee, so I know the Ecobee calls it the what's it called? The cooling differential temperature and the heating differential temperature. You can set it different for heating and for cooling. What this number is how many degrees is there between the temperature when it satisfies and shuts off versus it lets the temperature rise up until it turns on again. So whether you're in heating or cooling, you'll be going up or you'll be going down in temperature. But the deadband is, what's the difference between when it turns on and when it turns off? And again, here we're talking about single stage or 2-stage equipment that cycles. But this actually is relevant for inverter equipment as well, because on its lowest stage, it still is going to cycle off sometimes.
All right.
So
Which slide do you want, Steve? Let's hope they come out good. If they don't come out good, I'm gonna pull it down and
let's
share a screen.
Let's just hit the top one or the first one. I think this is what we want to talk about.
Yeah, it came out clean. Good.
Yeah. So this is some data logging I did on my house. The orange line at the top, that's your outdoor temperature. So just like you'd expect, it rises during the day, and you can see that right around 3:30 p.m. it hits about 92 degrees, and then it cools off. That's the orange line. The 3 lines in the middle are the one that's really flat at the bottom, the blue line. That's my set point. So it's set to 75, and then at about 10:30 p.m. it goes down to 74. The green line and the top blue line are just 2 different indoor temperature measurements. So the green one is the temperature that the Ecobee thermostat reports, and then the blue one is my Govee data logger that's sitting a couple feet up higher and a little ways away from it. But they're both in the living room. The gray temperature that says living room supply temperature, that's a temperature data logger that's in the supply duct boot on my shortest run. So it's 6 feet from the evaporator coil in the basement.
So that's like
And-
the supply temp all time. Okay. That's
Yeah,
cool.
exactly. So you can see, at the beginning of the graph, it's rising up from around 60 to around 70 degrees. And that's just from, warming up from the previous cycle. And then it shoots down really quickly. That's when the system comes on. So that
Right.
peak there is the moment that the system cycles on. And then, it drops down really quickly, and then it starts to flatten out at the bottom. And you can see this on each cycle.
Wow, you can see
And-
that coil getting really cold.
Yeah, I'm getting down. And the interesting thing is, as you go throughout the day, look at around noon, it's
Right.
around 50. But by the
Yeah.
end of the day, it's down to 45.
Yeah, it's getting down there. Yeah.
Yeah, it gets colder and colder during the day. And then the bottom of each trough, that point right at the bottom, that's when the system cycles off. And then the temperature in the duct just warms up naturally as the duct warms up. My system's in the basement, and the ducts are mostly between the basement and the main floor. So, that's where the temperature in the ductwork is going to migrate towards 70 degrees. That means that in that floor space, it's probably around 70 degrees. But the thing that's important to know here is that your cycle time and your deadband actually affect how the system operates and how efficient it is, and especially dehumidification. I don't have any data on dehumidification, but let's actually skip, I think, 2 slides ahead, Chris.
So real quick, let's answer this question if you can, Steve.
Yep. Go back. So Neil wants to know if this is an inverter. No, it's a single stage cooling system. Keep back up one more. Yeah. Okay. Go ahead, Eric. What were you asking?
No, that's what I was I want to know Neil's question, or the
Yeah,
answer
not-
to Neil's question. So,
Not an inverter. I'm just logging the temperature in the duct as it cycles off and on.
Yep.
So the temperature in the duct is changing just, when the fan goes off, whatever sort of convection is in there, that's what's going to warm up that data logger inside the register boot.
Which
All
slide do you
right.
want, Steve? This one, or you want to get another one?
No, I think we want to go all the way to the keep going. Next one. Yeah, this one right here. Okay. So I took a few of those cycles and I looked at how many BTUs are actually being delivered. So I subtracted the return enthalpy or energy from the supply energy. And I looked at, as the cycle starts, how long does it take for it to get up to where we're delivering, pretty much full capacity. And this is the 4 different lines are just 4 different cycles, just because I wanted to see how they all line up. They're not exactly the same, but they follow a similar pattern, right? You can see that by 2 minutes, we're delivering, maybe 2/3, 3/4 of the capacity, but it takes mostly about 5 minutes before it's kind of delivering at full speed.
What's the BTU of the unit?
This is a 3.5 ton, and you can see it peaks out right
Okay.
around 38. The
So-
airflow is too low on this. This is a house I recently bought, and it's got, ducts are not big enough for the unit, and the unit's oversized. You can see that, you on the previous slide, we were watching cycle time. It's running maybe 70% of the time on a day that's above design temperature for Minneapolis. So it's oversized, and the airflow is too
Little
low.
oversized, yeah, with that graph, yeah.
Right.
So we're looking for 42,000 BTUs.
Yeah, we're looking for 42,000. We really get about 39 out of this one.
That's normally what I see. Like 10 minutes runtime is where it just starts running nice.
Yep. So hit the next one, Chris.
I think that's our last.
But that's
slide, Steve.
impressive, though. That's
Oh, wait, no,
impressive. At 4 minutes, you're getting 35,000.
Yeah. Now,
I'm shocked.
I would like to see data like this from somebody that has a unit in an attic, because I think it's going to take
cool.
longer.
So my
My
dad,
evaporator coil doesn't get up to doesn't
Oh,
get up to
yeah.
130 degrees.
It
My
would also
dad-
You
Well-
got your unit in a wine cellar. Absolutely.
here's another query for you, Steve, to think about. How long does it take that coil to get down to temperature if you have higher airflow volume across it?
Mm. Right.
Yeah. What do you got it set at? 350 per ton or 400?
It's I haven't measured it in cooling, but I'm guessing that I'm maybe 1250, so I'm probably like 330 CFM per ton. Again, it's oversized. I'm too
Right.
low.
yeah.
Yeah. So that's what I think. There's a bar graph after this, Chris. I hope
I'm
I
gonna
put
send
it
him
in.
a true flow grid.
Yeah, this
yeah,
one.
there it is.
Yeah.
You'd think a guy like that would have a true flow grid to take home and measure some
What?
airflow.
Yeah.
We
I did the true flow in heating mode. I got the report, but I didn't run it in cooling when I did my true flow, so I got to do it again.
and it's a new house, right?
Yeah.
Yeah.
All right. So this is looking at if your cycles are, let's look at the 5 minutes. So depending on how long your cycles are, if I'm running 5-minute cycles regularly, that means I'm only getting about 70% of the full capacity, because I'm basically, for the first 2 minutes, I'm basically doing nothing. I got the compressors hot, the accumulator
Yeah,
is
you're,
hot.
you're,
Everything,
you're definitely
everything
not
outside's all hot.
dehumidifying.
Yeah, definitely not
You're-
dehumidifier.
Right.
Yeah.
I was talking about, how do I measure the dehumidification? I want to know when I actually start having drops of water go down the drain hole. That's what I want to know. I don't have that data, but
10
wanna
minutes,
get it.
man. 10 to 12.
you think
Well,
so?
When I do maintenances, I
Water-
start seeing that drain line dripping right around 8
Water-
to 12 minutes.
water out of the condenser coil drain, I'm sorry, out of the evaporator coil drain, does not equate to when it starts removing humidity from the air.
Right.
Right.
Well, here's what it does equate to. When the cycle stops, what happens to all the water that didn't go down the drain hole?
Right. It's going to set on that coil because surface tension.
In a 130-degree attic, what's going to happen to it?
It's going to set on that coil.
It's going to evaporate
Nope.
back into
Yeah.
the.
Nope.
It's going
Not
to go
only
back
if you're-
into the
only if-
ductwork.
Only if your fan is running.
Well, I'm going to disagree with that.
Okay.
We're putting a camera on a system in the attic. I'm really curious. I don't know.
So check
How
this
long
out.
it'll stay in
I've
there.
got an air handler in conditioned space, and when my air handler turns off, my return plenum, right underneath the coil, is at 90% humidity.
Yeah.
So what's up with that?
Vertical air handler.
Yeah.
Okay. So with vertical, you may get some natural convection going through that. But on your air
Oh,
handler,
like an infrared on like a cold can of like beer, you'll see the flow of
yeah, because
cooling.
you're gonna get cold air dropping down out of that, which is going to create high humidity in that right underneath that unit.
Right. Okay.
But what happens is that environment right around that coil forms a microclimate because you don't have any air moving through there.
Right.
And I learned
Right.
about this from a manufacturer down in Texas, and they went back to a system that had been turned off 3 days
Mhm.
in an attic in Texas, and they were still able to dump water out of the coil. Because it just forms a little climate around that, and the air doesn't actually go anywhere.
Yeah. So when I put a sensor
So-
in my return box,
Yep.
humidity's
I would
through the
bet you,
roof.
Eric. I would bet you that it depends on how leaky the ductwork is too.
Oh, that could
Because
definitely depend on
Ductwork
yeah.
is leaky. You're sucking attic air into the ductwork, which then goes into the house and out the bottom of the house. The stack effect plays into here.
But
Um,
you're sucking air into the ducts. You're not actually running it through the coil. There's still kind of like that little microclimate in that.
My
Well-
duct's tight as a drum, baby.
So it depends on where the leaks are.
Yeah.
Right. Do you have some near the cabinet?
Yeah.
If you have some near the cabinet, I would bet that microclimate is starting to dry out.
Could be,
So
but it's going to
Steve-
take a long time.
Right.
I don't think you're going to do it immediately. And you're definitely not going to do it on a normal off cycle.
And what extent are we talking about? A little bit of humidity coming off of the coil? Yeah, but
So let's
Quantify
go to Steve's best practices takeaway from his data.
Yeah.
run.
So here's
Sorry.
the upshot. You want to keep your cycles as long as possible and without having comfort complaints, right? If you set sometimes it's called the deadband, swing temperature, cooling differential temperature. It goes by names, but it's the difference between on and off. You want that to be as large as possible. I have mine set to 1 degree. It came from the factory by default with a 0.5 degree, which I think is way too low.
So-
If you have somebody who's not super sensitive to it's getting hotter, it's getting colder, might go for 1.5 degrees.
So Steve, to recap,
Like a single man in the house, right?
your data is stressing the point that a 0.5 degree differential is going to leave you with sensible cooling and not a lot of latent, and then you're going to cycle off. And you're going to come back on, and you're going to run 5-minute cycles, maybe on, off, 5 minutes, 5 minutes, 5 minutes. While if you go to a 1 degree deadband, you're going to run like a double that, 10 10-minute cycle.
When I changed mine from 0.5 degree to 1 degree, the cycles almost exactly doubled. It ran for twice as long. It was off for twice as long just by changing the deadband. And so, if you're moving from a 5-minute cycle to a 10-minute cycle, you're going from 70% capacity to like 85% capacity. So you're getting more capacity. And I think your dehumidification, your latent removal could double or triple.
That's amazing.
You got a cold coil much longer. It's draining down the drain hole for longer.
Yeah.
Yep.
So
Exactly.
Steve's big takeaway, make sure you're looking at your thermostats and making sure they're not set on a 0.5 degree differential. And they at least go for a 1 degree differential. Because if you're not getting the water out of the house like you could.
Man, that's crazy.
I bought a cheap thermostat at the Home Depot or someplace, and the deadband was defaulted to 1/4 degree. It was cycling like mad.
Now,
Yeah.
now, can we come back to this when we find out how oversized your equipment is, like in the future?
Yeah.
Because that really interests me. Because it does seem like it does short cycle just a little bit. So,
All right, I'm gonna
My
go ahead.
cycles doubled it. So my cooling cycles right now, in all the data logging, the shortest one was 12 minutes and the longest one was several hours. But they're mostly between 12 and 16 minutes or something. So I'm doing pretty good.
not bad. Yeah. Yeah. Okay.
But if I left the deadband default, instead of being 12 to 16 minutes, now they're 6 to 8 minutes.
So your deadband was set default was 0.5?
0.5. Yep.
0.5.
That's what Ecobee does. I don't know what other brands do.
We got one question in the chat, then I think we're gonna shut it down, guys.
Oh,
I
man.
gotta give Steve's big brain
Oh,
a
wow.
break before Monday starts. All right, so the question is, let's see, HVAC overtime.
Yeah. See, we got overtime in the chat. We can go overtime now.
But does the longer off cycle end up introducing more relative humidity with the heat gain?
I
I
don't
would
think so, because there's a maximum. The humidity that gets re-evaporated, whatever it is, it's going to happen, more as the cycle begins.
I think he's
And it's
talking
gonna taper
about
off.
the natural infiltration coming in
Oh,
from the heat gain and your humidity gain from outside. And I'm going to say that
Yeah, but
no, because that's
Filtration.
always coming in anyways.
Yeah.
yeah, exactly. The natural infiltration from outside is driven by the stack effect. So if it's cooler inside, it's coming in at the same rate.
Right.
The only exception to that is when you have leaky ducts and you've got the mad air situation, you're actually driving more leakage because the fan's running. That's, obviously a problem you got to fix a different way.
Yeah. So, I mean, your natural infiltration is going to happen no matter what. You still have the same amount of on and off runtime. It's just you're getting more humidity removal with that longer runtime versus shorter runtime.
Yep.
And
It's going to come in at a constant rate, and what you can do with the equipment is get more of it out.
yeah. And
Yeah,
the
all those
reason-
normal AC techs, Mad Air is a study they did in the 80s. This gentleman called Thule, right? Is that
Yep.
right?
and Moyer.
Yep.
Julian Moyer.
Yeah.
Yep.
That is a really good read, guys.
Yeah.
Yep.
So I can say that the thermostats, the dead band on the thermostat started narrowing because people wanted tighter and tighter control of their houses. And it's a selling point for the digital thermostats as opposed to the old mercury stats. So that's why
Yeah.
they started getting tighter. Now there is a point of obviously what's happening here sometimes is there is consequences to every decision we make, right?
Yeah.
And
The
if we tighten that up,
The thermostat manufacturer is sabotaging the equipment manufacturer.
well, and we're sabotaging everything by putting equipment that's too big. So if the
Yeah,
equipment was
right.
sized properly, it wouldn't be removing as much heat as fast.
No.
So it would
the
automatically
takeaway.
have
The
longer run
takeaway
time.
is this: if you really oversize the equipment, Eric, then you
See,
get
that's
short,
when I should
you
have
get-
closed the show.
You,
right
you
there.
get short run times.
Hold on,
You get
Michael?
short run times, and your
Oh.
BTUs are down. Did you see in the
Michael.
graph?
I'm coming down to put a 5-ton in your house. All right,
Let's do it.
Everybody's putting a 5-ton. in my
Jerry's
house.
gonna buy the equipment for me. We're gonna put it in.
All right. Thanks, Steve.
Thanks,
Awesome
Steve.
stuff.
See you guys.
Yeah, great show, guys. Thanks.